name is Jamil, and in this video I will be showing you how to construct a wide scanning range Michelson interferometer with a high fringe visibility. A Michelson interferometer is a common configuration used in optics. By using a beam splitter, we take a coherent light source and divide it into two beams. We then introduce a time delay to one of the beams by creating a path difference before recombining the beams. This delay produces a visible constructive or destructive interference. Therefore, this kind of setup can be used to measure the temporal coherence, which comes from the monochromaticity of the laser beam. Increasing the distance of the movable mirror allows us to further increase the range in which we can scan this delay time. A typical Michelson interferometer is constructed using two mirrors. However, when dealing with long-distance motion, flat mirrors are not the best choice, as there are imperfections in the motion causing small angular deviations. In order to eliminate these deviations, here we're going to substitute our flat mirrors with retroreflectors. However, the use of retroreflectors will also introduce a polarization change between the incoming and the outgoing beam. To obtain a high fringe visibility, we need to make both intensity and polarization between the two beams similar. Before we start, let's go over the components we are going to be using during this video. For this video, we will need a linear sliding guide for one of our retroreflectors, a motorized translational stage, which we're gonna use to scan the interference at any given position, a non-polarizing 50-50 beam splitter, two retroreflectors mounted on lens tubes, two XY translational stages, which we're gonna mount our retroreflectors to, one alignment laser, and one stable monochromatic laser with long coherence time, which we have already coupled into this fiber, two laser to fiber couplers with adjustable mirror, with adjustable focus, which we have pre-collimated using a monochromatic laser, one to feed the light into our system using a single mode fiber optic going through polarization pedals, and the other to acquire our output signal, which we're gonna connect to a multi-mode fiber optic. Four flat mirrors mounted on kinematic mounts, which two we're gonna use to align the laser with to make it the incoming laser beam parallel to the sliding guide, and the other two flat mirrors to couple the laser back into a fiber. One polarized beam splitter or polarizer, which will allow us to adjust our polarization, and a photo detector, which we're gonna connect to our oscilloscope. As a rule of thumb, we have already adjusted the height of all of the optical components such that they're similar once we mount our retroreflectors. Once you have all of the components ready, we can start building our setup, which consists of 5 parts. First comes the course alignment, which consists on making our incoming beam parallel to the sliding guide. Second part consists of coupling the output signal back into a fiber. This will allow us to go to the third part, which is going to be the final adjustment of the alignment using the oscilloscope. The fourth part, we will add the second retroreflector, which will create an interference. And finally, we will adjust the polarization to further maximize the interference. Let's start with the course alignment of the beam. As you can see, we have already fixed our linear motion guide to the optical table and mounted one of the retroreflectors on the card. We have also fixed the beam splitter such that once the beam splits in two, the reflected beam goes towards the direction in which we're gonna place our second retroreflector. We have also fixed our pre-collimated coupler, and we have connected it to a single mode fiber optic which passes through polarization pedals. We can now go ahead and connect our alignment laser to feed it to the system. And now we can introduce both alignment mirrors. And by guiding yourself using the holes on the optical table, we want to make two 90-degree angles such that the beam can go passes through the beam splitter, hits on the retroreflector, and then we can place a viewing screen to keep track of our angles. So again, using the holes to make sure we have a 90-degree angle, we're gonna place our first mirror, and we have to also make sure that the beam hits close to the center of the mirror. And the same thing we did for the first, we have to do it for the second mirror. Once you have your signal, you can go ahead and fix both the mirrors. Once the second mirror is fixed, we can observe the behavior of our signal as we move the retroreflector back and forth. Our goal is to find the position that minimizes the displacement of the beam as we move the card along the rail. As you can see on the viewing screen, we're having a diagonal motion. This means we have to adjust both the vertical and the horizontal knob of the kinetic mount of our second mirror. Let's start with the vertical displacement. First, I'm gonna adjust the vertical knob until we have only motion on our horizontal mode. As you can see, if we place the retroreflector on our initial position, if we move along, our signal is moving up. That means we want to adjust this knob and move the signal down. And we keep doing this until we only see in horizontal motion. That looks fine. Now we do the same thing with our horizontal knob. And we keep adjusting. Again, it's moving to the right. So I'm gonna move it to the left. And I'm gonna keep adjusting this until we have no motion. There you go. Once your signal is stationary, we are done with the coarse alignment. For the fine alignment, we will need to observe our signal through the oscilloscope. For that, we first need to couple the light back into a fiber. The coupling of a laser beam into a fiber has already been thoroughly discussed in a previous video. Therefore, here I will just give you a brief introduction. First, we have already switched our alignment laser to feed the monochromatic laser into our setup. So now we're going to connect our alignment laser into the back end of our multimode fiber, which is connected to our fixed receiving coupler. And we're going to introduce our two coupling mirrors by making two 90-degree angles of our red laser back into our beam splitter. And then we're gonna fix our coupling mirrors. Once we have fixed both coupling mirrors, we now have to adjust the knobs on our coupling mirrors so we can couple the light back into a fiber. To do this, we're gonna use our infrared card to keep track of our monochromatic laser, and what we want to do is overlap the two beams at two different ends. One before our receiving coupler and one after our beam splitter. We're gonna do this by adjusting the mirror that is always the furthest away from the viewing card. Let's start adjusting this mirror. So we place our viewing card in front of our coupler and overlap the two beams together. And now I'm gonna do the same thing, adjusting this mirror and overlapping the beams in this at this end after the beam splitter. And you're gonna keep doing this process until you have both beams overlapping each other at the both different ends simultaneously. Once both beams overlap at the two different ends, we can go ahead and disconnect our back end of the fiber and verify that we're receiving a signal. If you're not seeing the signal in the couple, that means that you have to go back and keep adjusting it until you get a signal. Once you have coupled the signal back into the fiber, we can go ahead and connect the other end of the fiber into our photo detector and the photo detector into our oscilloscope. Once you have connected it, you have to make a small adjustment to using the knobs on our coupling mirrors so to fully maximize our signal. Once you have adjusted and fully maximized that coupling, you have to also make sure the beam is going at the correct angle back into our fiber. To achieve this, we use a process called walking the beam. Walking the beam is done by offsetting the signal of using one of the mirrors and then compensate it with the other mirror. Since this process was already explained in the video I mentioned before, We have already maximized our signal by whacking the beam, and we can now move on to the fine adjustment. Once you have coupled the signal back into the fiber, it's time to move on to our final alignment. For that, this is gonna be just as we did for the coarse alignment, just now we're gonna use the oscilloscope. And just as we did with the coarse alignment, what we want to do is observe the behavior of our signal as we move our car along the rail. As you can see, we're losing a lot of light, a lot of signal as we move the car along the rail. So that means we still have to do some adjustment on our alignment mirrors to make our beam parallel to our rail. To do this, we're gonna work in two different spots. We're gonna be adjusting both alignment mirrors. And the way we're gonna do this is when our car is the furthest away from the beam splitter, we're gonna adjust the mirror that is the furthest away from our coupler. And when our car is closest to the beam splitter, we're gonna adjust the mirror that is closest to the coupler. Let's try right now and just move it the furthest away and adjust the mirror that is furthest from the coupler. Okay. Once you have maximized it, you move it again closer. And now, as you can see, the signal changed, so we're gonna adjust our mirror that is closest to the coupler, get our signal back, and we're just gonna keep doing the same thing until we have a minimal loss on our as we move the car along the rail. Now, as you can see, as we move our car along the rail, our signal we lost really small little signal. So that means now we are done with the fine alignment, and we can go ahead and add our second retroreflector to create some interference. As you can see, we have already attached our motorized stage up to the optical table, and we have already mounted our second retroreflector on top of our stage. Our goal in this part is to overlap the two beams so we can recombine them and create some interference. In this case, I'm going to use the viewing card to track the signals and then adjust the vertical and horizontal knob of our second retroreflector until we overlap both signals. Once you overlap the signals, you will see some interference. Once you have some interference, you can remove the viewing card, and we can now use the oscilloscope to further increase our signal. Let me just zoom this out a little bit. And now we keep adjusting our knobs until we fully maximize our signal. You can always guide yourself using the peak-to-peak value on the oscilloscope to know which direction you're going. We want to further maximize the peak-to-peak value. Once you have fully maximized the interference by overlapping the two beams, we can go ahead and move on to adjusting the polarization. To adjust the polarization, we are going to be using our polarized beam splitter, or you can also use a polarizer. Now we have to adjust our polarization in two sections of our setup. First, we have to adjust the polarization on our incoming beam. This is because even though we're using a non-polarizing beam splitter, the coefficients for transmission and reflection might be different depending on S or P polarization. To make our incoming beam either S or P polarized, we're going to place our polarized beam splitter or polarizer right in front of our coupler. And now we're gonna adjust the polarization pedals until we have fully minimized our signal. Now, as you can see, all of our signal should be being reflected towards this direction, and we should be getting almost no signal from going to our setup. Once we have made our incoming being either S or P polarized, we also have to adjust the polarization that is being introduced by our retroreflectors. What I'm gonna do is I'm gonna move this beam splitter, the polarized beam splitter, and I'm gonna put it in front of our receiving coupler. Now, to adjust our polarization, what I'm gonna do, since even though we have our couplers already pre-collimated, the collimation might not be necessarily perfect. So what we're gonna do is I'm gonna place our beam splitter up onto the farthest position. So that means that if we have fully maximized our signal here, we will have it also maximized on the other side. And for this step, what we're gonna do is we're gonna adjust the polarization being introduced by each of the polarizers. For that, we're gonna take you can take a blank piece of paper to block our signal from one of our retroreflectors. And once you have blocked the signal, what we're gonna do is we're gonna adjust this retroreflector, and we're gonna rotate it until we have fully maximized our signal. So I'm gonna go ahead and rotate it. Okay, that seems good. Now we're gonna do the same thing with our other retroreflector. We block the signal from this one, and we will rotate this retroreflector until we have fully maximized our signal. There you go. Now we have to verify that the signal is close, approximately the same for both retroreflectors. As you can see, they're both close to 1 volt, but we should be careful also by placing our polarizer or polarized beam splitter, as depending on the angle this can affect our signal. So I'm gonna go ahead and remove this. As you can see, right now we have a really high fringe visibility. In order to calculate our fringe visibility, what we need to do is take our maximum and our minimum, and we're gonna take the difference between the maximum and the minimum and divide it by the addition of the maxima and the minimum. Right now we have a maxima of approximately 7 volts. So as long as we have a minima less than 0.37 volts, we should be really high on our fringe visibility, at least at 90%. You can always try, since we rotated these retroreflectors slightly, this might move the position of our retroreflector, so you can always try to adjust here and see if you can improve this signal. Okay, since we can improve it a little bit. Okay, let's adjust this knob too. Since that might be it. So right now we have a really large fringe visibility. We have close to 90%, and as you can see, the visibility is being maintained. Actually, it gets a better fringe visibility throughout our entire rail of the guide. Now, again, as you can see, we still have a little bit of loss of visibility. This could mean that our collimation was not actually perfect. But even without a perfect collimation, we still have more than 90% fringe visibility. So that's it for this video, and thanks you for watching.